Okay, in this hour, I would like to talk something about inter-process communication, IPC. There are several ways for two different processes, no matter it is at the same host or it is on two different remote hosts. We have several different ways for these two remote process or just two processes to communicate with each other. And maybe you have never heard about IPC, but I believe you have tried some very strange things to that two different processes to exchange message. For example, you have two different processes, A and B, and the process A want to send certain messages to the B process, and the most convenient way for the process at the same host is to write a file and left some messages in that file. For example, process A could write some streams, some information, some integers, some numeric numbers in a file, okay? And then close the file. And you can let process B further then read such file to obtain the message sent from A, and so on and so forth, so on and so forth. However, using such kind of file-based way to communicate with each other, it is very inconvenient. Of course, write the file is convenient, but there are several inconvenient situations. For example, as long as the file is maintained or handled by the operating system, there's only one process can write that specific file at one moment. Okay, there's no way for two different processes to access the same file at the same time. So it would be better for those two different processes to figure out some way to read the file or write the file one by one. However, there's no any we say protocol for these two specific process to deal with the time access to deal with the access timing problem. So operating system, they provide several different way to do such kind of IPC. One of the way is shared memory. Okay, it is a very common way in Linux operating system to exchange information between different processes. For example, one process can ask the operating system to, for example, to register a block, a RAM block, okay, which is the memory block, and say, okay, I would like to share this block of memory with the other processes. And those two processes can share information by simply just write certain messages in the memory so that the other one can access the memory. Because access memory is much faster than accessing the file, right? So it would be even more quicker, more convenient to share information between different processes, okay? And of course, there are several other ways to share information, to send message between two processes at two different hosts. Okay, so socket, okay, it's right here. Okay, the next title. Okay, the socket. Socket is the most convenient way for us to exchange messages between two different hosts. Okay, so at least we have two hosts, right? Those processes are program running within the host. At least we need two process. Okay, so at the right hand side, usually we call it client process or server process, right? Client process is the process, the one that initiate the communication. As we mentioned before, usually client is the one who talk first, okay? And the process process is the process that wait to be contacted, okay? So usually has a fixed IP, as we mentioned before, and has a fixed IP address so that the client can find where to contact the server process. Okay. So of course, as we mentioned before in the last lecture, there's another way called P2P architect, which is a little bit different because there's no client, no server. All the peers act as a server and act as a client. Okay. Okay. So that is a process communication. So let's talk about how computer networks to do such kind of inter-process communication. So basically, let's take a look at this figure. Okay, we have a sender right here. Of course, in this figure, there's no specific sender or receiver. Just take one of the host as the sender and the other as the receiver. Okay. For example, the left hand side is the sender, right hand side is the receiver. Okay. So as we mentioned before, the protocol has several different layers. So that is application layer, layer 7, transport layer, layer 4, network layer, layer 3, then data link layer, layer 2, and physical layer, layer 1. Okay, so at layer 7, those two programs are your application, right? Your application. Right, that is your program, no matter it's written in Java or in Python or in C, C#, no matter what it is, that is your application. Okay, so at the bottoms here, layer 4 and layer 7, those are controlled by your operating system. So we have two operating systems, sender's operating system and the receiver's operating system. Okay, and layer 1 and layer 2, most of them are at the hardware, and of course there are some firmware or some software in the operating system which control the layer 2, but it's okay. We would rather in this way it's okay. Okay, so as we mentioned before, we have a message from the sender would like to transmit it to the destination, who is the receiver, right? So basically we should have a process right here, and now we have a very specific interface between layer 7 and layer 4. So we write it, we draw it right here. Basically, operating system and hardware is not what you can control, right? The only thing you can control is your application. So basically, you would like to send your message from your application to the remote process, right? So you would like to exchange. You would like to exchange virtually, right, among your process and the remote process. That is the MSG, right? MSG. But actually, you have to pass your message from your process, okay, to the underlying layer, okay, which is the program in your operating system which handles the transport layer protocol. There should be a gateway or a door or some place, okay, that you can dump your message to this specific entity, and that is what we call socket. Okay, that's what we call socket. When you want to send a message to the remote process, the first thing you have to do is to do registration. You have to ask your underlying transport layer protocol program in your operating system, okay, using certain API, application programming interface, or what we call library. Just as when you write a Java program, you like to write the file to a disk, right? Usually, you don't have to handle what exactly hard disk you have. It is a SSD or it is a hard disk drive, or what kind of operating system you use. You don't have to care about all the things. The only thing you need to know is that when you write Java, okay, there are some Java libraries, which is related to I/O operation. You should import or include those IO library. And the only thing you need to do is to initiate some entity. For example, in Java, because it is a OO language, right? So you need to create an object which represents the file, and you just operate those objects. So you don't have to know what exactly operating systems do when you write some string in a file. You don't have to do that. The only thing you need to know is which library you should include, and what function you should invoke, and what parameter you should use to write the string in a specific file. So it is exactly the same thing in socket programming. When you like to transfer a message from your process to the remote process, depending on your language, and take Java for example, you need to import, or you need to include the socket programming library, okay, which we will teach you after midterm, okay? And then in Java language, for example, it is again also an object, socket object, okay? You need to set several different parameters on this specific socket object, and you have to write some messages to this specific socket. So for example, write a socket, it exactly means you would like to send a message through this socket. When you read something from this socket, that means you receive the messages from this socket. So it is very similar to write a string in a file or read a string from the file. So it's exactly the same, okay? But you don't have to know what exactly the underlying layers. You don't have to know what exactly the physical layer media is used. You don't have to know what kind of network interface card is Wi-Fi or it is a wireless wire, Ethernet. You don't have to do that, okay? After the message has passed to the internet and forwarded by the routers, and then goes to here, right? Okay, and again, as we mentioned before, when you send your message from the layer 7 to layer 4, the message you send changes. There is a layer 4 header which is attached right here. So the name is segment, right? As we mentioned before, segment. So no matter how this segment has been handled by layer 3, layer 2, and layer 4 and route in the internet, okay? When the segment arrives at a remote host, okay, it is right here. So right here. So here again, we have H4 right here, and we have the attached messages right here. And after that, the transport layer program in the remote host, after it received the entire segment, it will read or parse the H4, which is the layer 4 headers, and see which process the message should deliver to. So after that, this message will go through this way, and again unpack the segment to message and send the message to the to a specific process. So from the perspective of the sender process and the receiver process, okay, on the above of the blue line, okay, which is the library API line, okay, it seems like that the sender has only need to prepare the message and send it to the corresponding socket, which is the object registered by the sender process. And then the socket magically can send the message to the remote socket, right? And the exact message will be sent to the remote process. So that is the message sending process. Okay, but however, as we mentioned before, actually the message has been packed to segment and handled by the left-hand side operating system and sent virtually to the right-hand side operating system, right? The right-hand side transport layer protocol. So from the perspective of layer 4, it received the message from the upper layer, and the left-hand side operating system and right-hand side operating system, they use segment to communicate with each other. And there are some important information has been stored in the H4. And again, so on and so forth. To the layer 3, there are several different there are programs in the layer 3 to handle the datagram, right? And at the right-hand side, the operating system, the network layer program at the operating system, they communicate with each other by using, as we mentioned before, that is the datagram, right? And so on and so forth, so on and so forth. So the underlying layers should serve the upper layer, right? So that is the reason why we call it the reference model, and it's a layered model. So let's take a look at the text in this page. Process send or receive message to or from its socket. Socket in Java, it is an object. Okay, socket looks okay. It's like a door. Okay, it's like a door. Sending process will send the message through this door, right? And sending process will rely on the transport layer infrastructure at its operating system, and the other side is the transport layer infrastructure at the remote operating system. They need these two different programs to communicate with each other using the information stored in the header layer 4 H4 to help them to pass the message from the left hand side to the right hand side through the socket. Okay. So actually, two socket involved. Okay, so I think that is the concept of socket right here. So we can take a look at the next page. Okay, as we mentioned before, there are tons of hosts in the internet, right? So there should be one we call address. It's right here, address, which can help us to specify which host we would like to communicate with. So on each socket, there should be some parameters to specify, okay, this socket is at certain host, and this socket is registered by certain application process. So there are two different things you need to specify when you create a new socket. One is which address, which host this socket locate to. And the other one is there are several different processes in an operating system, right? So which process is associated with this specific socket? So there's so we have two different things we need to do. What we call addressing a process. Okay, so we need an identifier to identify which socket it is, right? So let's take a look at the right hand side. Two things you need to specify. The one is the IP address. The IP address is used to specify which host the socket locate, right? So I think you should familiar with IP address, right? So here's an example of IP address. Currently we use IP version 4, right? IP version 4 has 32 bits field to represent the IP address. So theoretically, it is a 32-bit integer theoretically. So the smallest number is 0, right? The largest number by using 32-bit is 2 power 32 minus 1. Okay, so in total there should be nearly 4 billion unique IP address. 4 billion is a very large number. However, currently, all those 4 billion unique IP addresses has been distributed to different ISPs and different university, different companies. So currently, we already run out of all the IP addresses. So that's the reason why we need to migrate to IPv6. Okay, we'll talk about this problem later. Okay, so that is the way. How do we specify a host on the internet, right? So I have to specify this value in on your socket. Okay. So the other one is how many process can be how many socket can be created on an operating system. So currently the port number has 16-bit. It is a 16-bit integer in your operating system. So theoretically, the smallest number should be 0 and largest one should be to this one. And this number is about 6,500. So theoretically, your operating system can distribute those numbers to different new created socket. Okay, so that is when you create a socket, you need to specify the IP address, and you need to specify the port numbers. That is the number is called port numbers because it's like a port, right? You can input output some messages from this port. Okay, so you usually have port numbers, and theoretically it has 65,000 different numbers. However, you can take a look at this port number. Okay, and right here we have some port number list right here. And of course, different application layer protocols, they have some they have some I say they occupy some certain port numbers. Okay, so for example, right here's a list called well-known ports. Okay, well-known ports, and number right here is the port number in the range from 0 to 1033. Okay, they are usually known as well-known ports or system ports. Okay, they are usually used by for example, system process or some very commonly seen servers. For example, HTTP servers. For example, email servers, something like that. So when different new applications protocols they are invented, they will try to find a fixed port number so that you can find which port that the server process use. Okay, so there's some list right here. For example, we can take a look at number 80, right? Number 80, okay, it is a well-known port number which is used by HTTP, which is the Hypertext Transfer Protocol. That is the web server that you use. okay, port number 80, okay. And for some interesting port like number 20 and 21, right? It is file transfer protocol. If you like to transfer file from one host to the other host, you can set up a file transfer server. So the server will open two sockets. One is at number 20, the other is at number 21, something like that. Okay, so in the browser, your browser is a web client, right? So when you type http:// IP address, okay, usually you specify which socket you would like to connect it to at the remote host. The remote host IP address is 128.119.245.12. Okay, and usually you don't have to specify the port number because HTTP server is a well-known port, well-known service. So usually the service will be registered at port 80. The socket number is port 80. So if you simply just enter the IP address in your browser, this port is good enough. But if you would like to specify the port number, you can just simply enter 80 at the end of your IP address. Okay, so I think that is the addressing things about the socket. Okay, so the next one we'd like to talk about is when you design your own application layer protocol. So again, it looks like this, right? You have a message. You like to pass the message to the underlying, the right hand side, right? And you have the therefore there should be one socket right here, and you pass it to the underlying transport layer, and so on and so forth. Okay, so let's simply just write it in a more simplified way. Okay, you have to write your own application layer protocol to specify what information has been included in your message, right? For example, if you want to write a new application layer protocol, which is a gaming protocol, so you have to specify, for example, your position, right? So there should be a coordinate, right? There should be two numbers, x, your position at x and y axis, right? So how did you represent these two numbers? They should be in binary, or they should be written in hexadecimal, or written in decimal, or written in binary, for example, a string. It doesn't matter. As long as the left-hand side, which is your client, and the right-hand side, which is your server, as long as the client and server, they know how to parse the messages. It really doesn't matter how do you design your own message format, right? So there are several things you need to know before you design a protocol. First, you have to define how many different types of message you would like to exchange. For example, if you want to request a certain service from the server, maybe you need two different type of message. One is request. So you have to design your request message. And after that, when the server responds such kind of request, you need to define the other type of message, which is called response message. Okay, so in the message, two things you need to deal with. The first is the syntax, the other is the semantic. The syntax defines how many different fields. For example, okay, let's just simply draw something just for example. For example, it is a very large, for example, it is a very large message you would like to transmit from your client to server. Okay. However, there are several different information you would like to exchange or share with your server. Okay. For example, you have 3 different information you would like to share with your server. Okay. So I have 3 different, and each of the for example, each of the information is delineated right here. Delineated by, for example, an enter. Enter, right? And enter. Okay. The first information, maybe that is your position, right? You play a game, that is your position. But you have to know. You have to let the receiver, the server know the first part is the position. So maybe you have to write some specific characters or strings, right? For example, you write 3 specific byte, which is POS. So let's specify all the following section is the position that I would like to share with you. Okay. And the second part is usually, okay, I say usually, you should specify what is the length of the value attached right here. So for example, you write, 4, right? Maybe that means 4 bytes. That specific number means 4 bytes. There are 4 bytes. So I can draw 4 bytes right here. 1, 2, 3, 4. And maybe the first 2 bytes is the coordinate of your x-axis. The other one is the y, the value. And those values are in maybe in integer or in hexadecimal number or floating point. It depends on your design. And that is the first message you would like, first part of message you would like to exchange. And the second part, maybe that is another thing. Maybe that is blood, BLD. That means the blood of your character. Okay, maybe that is 2 bytes value right here, so that there should be 2 bytes. 2 bytes can maybe that is 1, 2, 3, 4, something like that. You can continue design different we say semantics or syntax, by it's on your own. It's really on your own. It really doesn't matter, as long as the sender, which is your game client and your game server, know how to parse this message. It really doesn't matter. So here we have a clue right here that usually when you design different part of your exchange messages, type, length, and message, that is value. Okay, type then value. That's a very common way to design your block. Okay, for each block, for example, the type is POS or BOD. The length is what is the value attached after this specific field. Okay, so that is the field you can design, and you have to design different delineation. And then that is the semantics. After, for example, after the server receives such kind of message sent by the client, the server should do something, right? Do some action, right? To, for example, when it receives the new position, maybe at the server side, the server should update the current position of your character, right? Or the server should send or synchronize such kind of information to all the other players in the same game server, for example, something like that. So in your protocol, you have to define what kind of message you can send and what action should be taken after the server or the client or anyone in the communication should do after it received such kind of messages. Okay, so that is the rules. Of course, you have to define different rules. Okay, as I mentioned, when you receive certain messages and you do certain actions, right? However, I think the other thing important is that you have to specify what if something goes wrong. So you have to do error handling or exception handling. That means because we communicate with each other on the internet, right? As we mentioned before, the message can be lost, the message can be delayed, the message maybe the host is disappear, maybe because the power outage or something like that. So when you send a message from your socket to the internet, sometimes the message may not be able to receive by the receiver due to some reasons. So you have to, in your protocol design, you have to design certain error handling or exception handling mechanism so that even though your message is not sent, it's not well received by the receiver, okay, you can still keep alive, which I mean that. Okay, you can still keep alive. For example, when you send a message and you wait for example, 10 seconds and no one responds, and maybe that message is lost, right? So maybe you have to set a clock, 10-second clock, and said, okay, after 10 seconds, I did not receive any response. So maybe I should send the message again to my peers, to my clients, to my server, something like that. So I think that is one of very important things. It is not just design what you expect. You have to design everything which is unexpected. Okay? Okay, and at the right-hand side, we have two different type of protocols, which is open protocols or proprietary protocols. In the early days, because those researchers that want to share information with others, right? So they send their protocols to a public place, which is the RFC, request for comment. So those RFC, they are open to the public. You can exactly know what is the fat message format, what is the field means, what is actions should be taken. Everything is open to the public. Okay, so it allows interoperability. So for example, if you download the HTTP protocol from the internet, which is open to the public, and you can follow the HTTP protocol to create your own browser, because all the rules that a browser should take are written in that HTTP protocol document. Okay. However, there are some proprietary protocols, for example, Skype. In early 2000s, Skype is one of the very first few voice over IP company, and it has a very nice we say VIP quality, but we don't know why Skype is so good, because the protocol is proprietary. We don't even know what is the very first byte means in its protocol, because it is hidden. It is just some binary bits which we don't know. Okay, that is because Skype would like to protect itself from being copied by some others, right? So we have open protocols, we have proprietary protocols. Okay, as we mentioned before, let's take this one to here. Okay. Again, as we mentioned before, we have different layers, right? We have layer 7, we have layer 4. So when we learn how to write a layer 7 protocol, we have to know what kind of service has been provided by the underlying transport layer protocol. So in textbook, it says 4 different services can be provided by the underlying transport layer protocol. Okay, so first one is data integrity. Okay, as we mentioned before, for some application, when you send a message down to the transport layer, right, it should attach its therefore header, right, to create the segment and pass it to the corresponding operating system at the right hand side, right? So there are some some applications, for example, file transfer, web transactions, or email. When you send an email, right? When you send the file in an email, attach a file in an email, the file should be exactly the same as what you transfer, right? You wish the file received by your receiver should be exactly the same as the file you send, right? No any bit should be different, right? Every bit should be different. Sorry, every bit should be the same, right? Every bit should be the same, right? So when you send the message down to the transport layer, okay? For example, you have 1 million bits want to send to the socket, okay? As we know, the underlying layer 3 is packet switching, right? So the 1 million bit message should be divided into several different small chunks, which is called packet or datagram, right? So those packets will be routed or be forwarded in the internet, and at the end will be reassembled at the receiver, right? So when those small packets, those small chunks has been transmitted on routers, it is possible that some routers might discard or simply just drop some of the packet because the router is so busy, the queue is full, so some packet might lost. Okay, but it is not your responsibility to do such kind of checking, because when you did send the message from your socket to your transport layer, the transport layer should help you to deliver the entire message, even though it is divided into several different small packet and routed by router. Okay, no matter what. Okay, your operating system and the corresponding operating system and the receiver, they should communicate with each other by using the H4 ladder to guarantee all of the messages sent from the socket should be delivered to the right-hand side socket and to the receiver process. It's their responsibility, okay, at the transport layer. So right here, some applications require 100% reliable data transfer. So there are some part of the transport layer program, they will help the upper layer process to do so. Okay, that's called data integrity. But we will not talk about how those two different two operating systems, two transport layer protocols to do such kind of functionality. We will talk about it in later chapter. Okay. However, take a look at this one. There are some applications, for example, audio. Okay, so for example, the audio likes this, right? You have several waves like audios, and then we convert this audio by using digital signal. For example, that is 0 and 1. For example, we just simply draw some digitalized wave. Okay, and here that is a small chunk, a small voice packet. Okay, small voice packet. Okay, for example, that is 1 second. Okay, you will divide your entire voice into small chunks, right? And each chunk, maybe it has several, it has 1 second voice, and we'll send the voice through the socket from left hand side to the right hand side. Okay, and if the second packet is lost, if the second packet is lost, okay, the socket at the left hand side receive 1, 2, 3, receive 5 parts of the voice and send it to the socket, right? And at the right hand side, the socket should receive again 5 different voice messages and display it at the right hand side, display them at the right hand side, right? But if the second one, the second voice packet is lost, is it necessary for the 2 transport layer program at 2 different hosts to negotiate with each other? Say, okay, at the right hand side, okay, currently at the right hand side, it is playing the first packet, but the second packet is lost, right? So when it comes to here, try to play the second part of the voice because it is lost. So it simply just plays some random voice or some silent voice right here. And then if the third voice sound packet arrives, and it can continue to play the third part of the voice and the fourth and the fifth and so on and so forth, right? So because some application, once you missed some timing situation, okay, because you have to play the second voice packet at the moment after you finish the first packet, voice packet, right? So if it is not there, if the second packet is not there, you simply just let the time goes by, right? And play the third one, fourth one, and fifth one. So it is not, so for some application, it is not necessary to let the transport layer protocol to negotiate if we like to retransmit the second packet. No, it is not necessary to do so because some application can tolerate such kind of loss. So as you can see that 2 different applications, they require different quality of the data integrity. Some application cannot tolerate any loss. So the file transfer should be 100% reliable. So every single bit sent from the left-hand side socket should be at the right-hand side in order, and no any bit should be lost. But some application, they can tolerate loss, so it is not necessary to need to retransmit the lost packet. For example, audio or video streaming application. So that is data integrity. So we have different level of data integrity can serve the upper layer application. Okay, the next one is timing, and the right hand side is throughput. Okay, when you send the message from the socket, is it guarantee, or is it guarantee that you can send the message within, for example, 10 milliseconds? And as we mentioned before, because currently we use packet switching. So we have routers and we have queues. So we have several different types of delays, right? So in current internet, the underlying infrastructure, which is packet switching, does not allow us to do such kind of guarantee. There is no guarantee that if I send a message from the left-hand side, we do not guarantee anything that how many milliseconds it takes for the message to transfer, to route in the entire internet. And when it arrives to the right-hand side socket, can it be less than 10 milliseconds? No, we cannot do such kind of guarantee. We do not even know how many milliseconds it takes to do such kind of transmission. So the timing is currently not guaranteed in our current internet infrastructure. But think about one thing. If we still use circuit switch, right? So that means we have a dedicated line from the host to the sender, to the sender host, to the destination host, and all the lines, no matter it's copper lines or it is fiber, it is dedicated resources for this specific source and destination. So at that time, if we use circuit switch, the timing can be guaranteed. At the right hand side, again, throughput can be guaranteed. Okay, but however, we use packet switch right now, so the throughput and timing is not guaranteed in the current internet. Okay, so last one is security. Okay, when you design your message and you send it to the underlying transport layer, you can decide to encrypt your message, or you compress your message, or you can do whatever you want when you send a message, as long as when the message has been delivered to the receiver at the right hand side, the corresponding receiver knows how to encrypt, how to decrypt, or how to uncompress the message you sent. So currently, therefore, which is transport layer, do not provide any security functionality. So if you want to do encryption, compression, or any encoding things, you have to do it by yourself at the application layer. Okay, so that is it. So here you can take a look at this table. Okay, for file transfer or download, there are some applications they do not tolerate any loss, any bit errors. So you have to provide no loss transport layer. But for some applications like here, gaming, video, streaming, real time, they are tolerant to some loss. Okay, and again, text message does not should have no loss. And how about throughput? And usually they are not guaranteed. But here the test will give you some information about if you would like to do real-time audio or real-time video, the amount of throughput you need is between these numbers. But however, in the current internet, we do not guarantee such kind of throughput. And again, time sensitive. When you receive email, you really don't care. The email the email takes you 20 milliseconds or 30 milliseconds to transmit the first bit to your email client. For example, in 20 milliseconds or 10 milliseconds, you really don't need that. Okay, and for some, but the interesting thing is that right here, when you see live streaming, okay, live streaming, it depends on if you want to interact with the live streaming content. If you do, then usually few seconds delay is tolerant for human beings. But if you want to see some really high interactive games or real-time audio or video, 10 milliseconds is large enough, because if the delay is larger than 10 milliseconds, human beings are very sensitive and they know the games are lagging, something like that. Okay, we stop right here, and we'll talk about several different application layer protocols in the following class.